Okay, let's get started. So I hope everything was okay with the quiz yesterday. So we had some, so I think what we're going to do next time, so I was informed that the grade scope has an option of having a quiz where you can just log in within a 24-hour window, and then you just do it for a fixed amount of time, and then there's a cutoff time. So I'll research into that. I'll see if this is more convenient for us than what we had yesterday, because it was a little bit of work for me and for you to arrange all this quizzes in different times. But otherwise, I think it was okay. I'm a bit worried that I only have at the moment from two groups, two sections, 63 submissions, and should be like 80-ish students. Maybe some of them already dropped. But so is everybody, all of you here who are online now, has everybody taken the quiz yesterday? So is there anyone who hasn't? Okay, yeah, okay, good. Yeah. If you haven't, let me know. Okay, good, thank you. Okay. So yeah, I'll post the solutions soon. So one of our TAs, Emma, like she'll be grading the quiz for all of you, and I'll give your email. So if you have any questions, you can contact her about the grade. So it will be what, 20 points, each problem 5 points. Yeah, that's pretty straightforward. Okay, so last time we finished with the triple product. All right, so as we see here, the so triple product is formed by making a dot product of a vector and the cross product of two other vectors. Using the definition of cross product and dot product, we have shown that you can write triple product as the following determinant. So you simply write the components of the vector, of each vectors in rows of the 3x3 matrix, and then calculate its determinant. Also, we have proven the cyclic symmetry. So if you permute A, B, and C in triple product by side cyclically, which means that you replace A with B, B with C, C with A, and you can do it 3 times, and then the answer does not change. And finally, geometric meaning of the triple product is the volume of a tetrahedron of the parallelepiped, which is built on these 3 vectors. Yeah. Now, let's talk about today about parametric equations of lines and planes. So you will see that instead of trying to solve some complicated 3D geometry problem, it's rather easy to use vector calculus, vector formalism, to understand how to define first lines, then planes, and then we'll talk about surfaces. So using using functions of many variables. So let's start with lines. Lines in 3 dimensions, and so say we have the set of Cartesian coordinates. X, Y, and Z. And then the line goes somehow like this. Okay, so now our task is to describe its equation or equations somehow, and we'll use vectors to help us to do so. So let's pick a point on the line, absolutely arbitrary point anywhere in the line, right? And then let's draw a vector that connects the origin of the coordinate system and that point. And let's call this vector R0, R0. Again, it can be chosen absolutely arbitrarily. There is absolutely no reason to favor one point as opposed to another. And now let's pick a point A on the line, different from this point that we have selected, and that point A has coordinates x, y, and z. Okay. Then let's draw a vector that connects, whose tail is at the endpoint of the radius vector R0, and whose tip is at A. Let's call this vector A little. Okay. And now there's a simple vector addition formula that tells you that if you take, if you connect O and A, right, we can call this R. So R is equal to R0, R0 plus A. Right? So that's a simple vector addition. And clearly, you can do this for every point on the line, right? So you can put point A over here. You can put point A over there. You can even put point A at the same location as the endpoint of R0. The thing that it would still work, right? So there always will be some vector little a, which we can pick such that this is true. So now let's select a unit vector. Let's say vector v is the unit vector in the direction a. Right. So it's here it would look like this. And since we know that if you use scalar multiplication, right? So for every point here on the line, right, we can always, so for every point, for each point A on the line, there exists some number t, which is real, right? Such that this vector A is equal to t times v. So in other words, t is a coefficient, is the coefficient, excuse me, that it's a proportionality scalar. It's a coefficient between A and B. So this way that every point on the line, x, y, and z, is parameterized by the following, right? So then you can just say that R is equal to R0 plus V times T. So this is the parametric equation for the line. Of course, you recognize it from over some interphysics class, right? So here, let's say, well, you can interpret V as the velocity vector, T as time, and R0 is the initial position. I even deliberately use the same notation as in physics literature, right? So you should think of sort of point A as sort of sliding along this line, right? And then at constant velocity, and then the position will be determined by this equation. Oh, sorry, yeah. There's a, this is that's right. So this is so-called quantifier of existence. So if you haven't heard this before, so the inverted E means there exists, and then what does this mean? it's not the quantifier in logic. So E, so the reason why it's, as Sharon is saying, it's backwards E. So E is E from exists. Now I draw another symbol. It's inversion of which letter? So you can, here you can do the mirror reflection of E. You'll get the real E. So if you do mirror reflection of this, you'll get A. Right, and this, the symbol means that for all. Right, so these are so-called quantifiers. There's existence quantifier and for all. Like it's just these two. Sort of, it's used widely in math literature. They just simply save you a lot of space, so you don't have to write it down. So and then for each, instead of for each, or I could have said, I could have replaced this. And then on the second thought, yeah, I thought that you might know the notation, and then I forgot about that on the second line. Yeah, so that I can replace this with the symbol. So for every point A on the line, there exists number T in R such that A equals T. Okay. Other questions? Good. So now you can also, since so radius vector R has components X, Y, and Z, right? R0 has components X0, Y0, Z0, and same with V. So we can write it like this. We can say that X is equal to X0 plus V, and then let's denote it V. So Vx, Vy, Vz. Yeah, it's the same thing. So these are the three. So one vector equation is worth three scalar equations, right? So therefore, the line in 3 dimensions is given by 3 equations like that, right? Well, we'll talk about another presentation in a second, but just to remember, so remember when we talked about planes, right? So plane was given by a simpler equation. Say plane, which is parallel to the xy plane, was given by equation z equals a constant, right? But turns out that lines are a little bit more complicated. So it's a little bit more complicated to describe a line in 3 dimensions than a plane. Why do you think this is the case? So for a plane, we had one equation. For the plane, we had one equation, and for the line, we have well, 3. But in fact, we can get rid of parameter t, and then there will be 2 equations. Okay, so Julian's saying because lines can span 3 dimensions. Well, planes also can span 3 dimensions, right? So the plane can be, I mean, it's 2-dimensional, but it's like, so right. So we need to count dimensions carefully. But so let's try to understand it. So in other words, what do you need to know to describe a plane, right? So there's a plane, right? And then, well, we know that we'll talk about this in for 10 minutes. Like if you have a plane, then there's a vector which is orthogonal to it, right? And it just suffices to give one vector, right? And we just need to know where this thing is located, right? So as long as you know the coordinates of the vector, which is orthogonal to the plane, the other thing you need to know is some point on that plane, and that's it. But with lines, we wouldn't have to know the surface. That refers to what? So like, can you elaborate a bit on that? Doesn't this right? Yeah. So I think we're saying like it's give rise to a specific point. So you're referring to the plane or to the line, Clarice? Okay, sure, that's right. Yeah, so with the plane, right, you just give the specific, right. So once you know, yeah. So I think what you're saying is that once you know this orthogonal vector, and then that gives you a family of planes, but then you just need to anchor it to some specific point, and then that fixes the plane uniquely, right? With the line, in a sense, you think of a line like this, like you have, there's a line on the plane, right? Like I drew a line in my notepad, and then it's not sufficient. So once you do the specification of the plane, it doesn't fix the line uniquely, right? Because you can still rotate this along this axis, right? And that would still give you the same line. So you need some extra conditions to define that line. So maybe we can look at some more specific examples. So say we have a 3D coordinate system, and then I'm looking at the plane z equals 0. And then there's a line which goes along the x-axis, right? So given what we just said now, which equation will describe this purple line? Which I think the way I do it is y-axis, I'm sorry, not to confuse you with that. Yeah, so this is x, y, and z. So the green plane is described by equation z equals 0, which equation or equations so either give me a vector equation or give me the three scalar equations, how to describe the purple line. X equals 0 and z equals 0. Yes, Julian, very good. So yeah, so it's really, that's what it is, right? Because this line, if it projects down to sort of, yeah, so it's indeed that's how it works. So the line is given by x equals 0, z equals 0. And then if you want to specify something about y, well, you can, right? You can just say that y is equal to some, you have vector j, right? So you can just say y equals to t. But this equation, it doesn't give you any new information. What you're doing is just relabeling this this coordinate, right? So in here, you just say that, okay, the t changes between plus infinity and minus infinity. Right, but sort of the essential part, essential ingredient for this construction are these two equations, right? So, as we just discussed, sorry, there's some construction going on. So equation z equals 0 fixes the plane, and then inside that plane you need another equation that fixes you the line. So in this example, it's sort of it's straightforward, right? So z equals 0 equation is only part of the construction, and then you also need to say that x equals to 0, or if you have some different line, right? Say in that plane, say a line that goes like that, then you have some linear equation between x and y. Yeah, that's right. So other reason to sort of, if you another reason to count, sort of another way, excuse me, to count these equations is this. So plane is two-dimensional, and it lives in three-dimensional space. So the number of complementary dimensions, so the number of dimensions in space minus the number of dimensions on the object itself is 1. So that's why we say that planes have, this is the new term here, codimension. Codimension 1. So codimension is this, is the number of dimensions of the R3, right? So it's a three-dimensional space that comes from R3 minus 2, that's the plane, because the plane looks like R2. So this is the new term. And lines have codimension 2, right? Because it's 3 minus 1. So these are so-called codimensions. So in other words, codimensions, they count the number of equations, number of constraints that you need to impose in order to describe the space as sort of the shape. Well, this counting has to be done carefully because it works directly if your equations are linear, like we're doing right now. If equations become polynomial, then it's a bit trickier. And so so this is dimension, right? So plane is 2-dimensional and line is 1-dimensional. Yeah, so since plane has codimension 1, it requires one equation to specify its location and orientation, and line has codimension 2. That's why we need 2 equations here. Any questions? Okay. Good. So let's. I hope that that was helpful. And of course, like yeah, and then this count goes in. It works in any number of dimensions, right? So yeah. The then you can sort of adopt this formula a little bit to. So say you have a line, and then there are 2 points on the line. One point has, let's say it's R0, and this one is R1. And this is the origin of the coordinate system. I'm not going to draw the full, all the vectors. So say we want to start, we can look at the segment here between R0 and R1, and there's some point R here, right? So there is another way, if you know explicitly the formula for R0 and R1, you can find R like this, right? So you can say that R is equal to, we can parameterize it using a parameter T, which varies between 0 and 1 in this case. And you can put it like this, so it's equal to 1 minus T times R0 plus T times R1. So let's see what's going on here. When T is equal to 0, the second term disappears, and then this also disappears, so R is equal to R0. And R of 1, when T is equal to 1, then the first term disappears, and the second term gives you R1 is equal to R1. And for T between 0 and 1, it's given, the answer is given by the formula. Right, so this equation conveniently describes you the line segment. Between these two endpoints. And I'm sure you'll see this formula later when you take higher classes, right? So these are so-called, so this is so-called straight line homotopy between these 2 points. So homotopy is another term. Maybe let me type it here in the chat window. It's used in topology. So essentially, it's something that allows you to take one shape and then continuously deform it to another one. So using this straight line homotopy, you can show, for example, that a mug, like a coffee mug, can be continuously deformed into a torus. Like I have one here, into this thing, right? So they are similar because they have a hole in them, right? And then, well, here there is no hole, it's just the shape. So these 2 shapes are homotopic to each other. And the way it's proven in topology is you construct explicit formula explicit transformation like that. Any questions? I'm glad that nobody asking questions like, is it going to be on the test or something? No, this is not going to be on the test. Okay. Yeah, so that was the straight line. Okay. Now let's talk about planes. So as I told you before, you can look at the plane in terms of its normal vector, right? So say there's a plane, and then pretty sure put do not disturb. Okay, so and then let's just fix any point on the plane. So the idea will be the same, right? So we'll put a line. So there is some segment on the plane, or line segment on the plane, and then say there's a point here. So say this vector is R0, and this is a point P, which is on the plane, right? And say this is R. Right, and so we have arbitrarily chosen 2 points on the plane and connected them with a piece of straight line. So this vector here is R minus R0. I just put the arrow in the middle so it's easy to see. And as we just discussed, we need to give the plane sort of to describe the plane in 3 dimensions. It suffices just to pick a point where it's anchored, let's say this one, R0, and the vector which is orthogonal to the plane, or in other words, is normal, right? It's a normal vector, so we call it N, right? Which makes 90-degree angle with everything here, but in particular with this line. So then it suffices to simply write that the dot product of this vector n times r minus r0 is equal to 0. Right? And that's it, right? There's one equation. So it's because the dot product is scalar, is a scalar quantity that simply gives you one equation. Right. So if normal vector has components A, B, and C, then you can rewrite this as A x minus x0 plus B y minus y0 plus C z minus z0 is 0. And if you remember, I announced the equation for the plane in slightly different form. So let's open the parentheses and collect the terms. Then you can write it like this: that ax plus by plus cz plus d is equal to 0, where d is, well, it's just the remaining stuff, right? It's minus ax0 minus by0 minus cz0. So that is so these are 2 different equations. Well, this is the equation that parameterizes the plane. Right, so the plane that we had, example that we had before. So if you have a plane here that passes to point z equals say 6 and is orthogonal to the is parallel, excuse me, to the xy plane. So we can pick vector n. Can pick vector n, well, which has coordinates 0, 0, 1, right? It's a essentially n is the vector k, goes along the direction, and then we need to have this vector r naught, right? So vector r0 will have components 0, 0, and 6. And then, well, how would you describe equation? How would you describe any point on the plane? Well, you just do well, you just write this equation, right? So it's so in here, in this case, a and b are equal to 0, right? Yeah, and then so then we have, well, let's just put it to 0 times x minus 0 plus 0 times y minus 0 plus 1, right, times z minus 6 equals 0. So therefore the equation for the plane is z equals 6. So yeah, so that works. Now let's look at some less trivial example where plane is not parallel to anything, to any axis or any coordinate plane. Take, let's say we draw this tetrahedron, right? So we can take the so let's say there's a plane that contains this triangle, which connects points, let's say here it's on X, we have, alpha, beta, and gamma, right? Where alpha and beta and gamma is just some positive real numbers. Yeah, and then our task is to find the equation for this plane, right? Okay, so quick question: how do we find how do we find the we just know that to find the plane, we'll roll it back a little bit. We need to find any point that it's anchored to, and then we need to find the normal vector. So the first question I can answer myself, it's really easy. Well, we just pick any point. For example, this point alpha, which is actually, should write it as alpha 0, 0, right? And then just draw the radius vector r0 to that point from the origin. So r0 will be 0, 0, alpha. And then at point alpha, we need to find the coordinates of the vector, of the normal vector to this plane. Also, keep in mind that we don't need any conditions on n. It doesn't have to be unit length or anything. It can be any length as you like, as long as it's not 0. It will give you the description of the plane just fine. So how shall we find this vector n? So we need to find a vector that is orthogonal to the plane. We know a very efficient way to do that. Yeah, absolutely, a cross product, right? So cross product of any two vectors that lie inside that plane, and luckily we just have them at our disposal, right? So one vector would connect points alpha and beta, and the other vector will connect points alpha and gamma, right? So we can just say that our n vector is equal to what? So it's vector alpha beta cross vector alpha gamma. Okay, and now we can do the cross product formula I, j, and k. So what are the components of vector alpha beta? So alpha is 0, 0, 1, beta is 0, beta 0, and gamma is 0, 0, gamma. What should I write in the second and the third line of the matrix? It's just the vector, which is this vector here, which goes from alpha to beta. So this is alpha beta. What are its coordinates? Minus alpha beta 0. Sure, absolutely right. So you literally subtracted. There is nothing fancy here, right? So you subtract 0 minus alpha. Well, let's do it once, right? So it's coordinate alpha beta will have coordinates. So it's 0 minus alpha, beta minus 0, 0 minus 0, which is minus beta 0, minus alpha beta 0. How about the alpha gamma? Just need to do the same with alpha gamma. This one. Yeah, absolutely. So minus alpha, 0, and gamma. Okay, so can we calculate this cross product? What will be the components of this vector? Just need to do the determinant of the 3 by 3 matrix, right? Is the question clear, or we're just doing the yeah? It just well, here's the determinant, right? We need to calculate do the expansion of this determinant along the first row, and identify the good. So Han is writing beta gamma, alpha gamma. Yes, that's correct. Right? So beta gamma, alpha beta. Yes, yeah, alpha gamma, that's right. So yes, alpha gamma and alpha beta. Yes, does everybody agree? So you need to just, with I, you calculate this minor, so this is beta gamma. With J, you're calculating with a minus sign, the minor from the first column and second, and so on. So see, there is some symmetry here, right? So in particular, when alpha and beta gamma are the same, so like this sort of plane goes in 45 degrees in some sense, then all these components are the same. It wouldn't be just a multiplication process of the product Clarissa, don't understand the question. Also, Fox, if you can send it to everybody.
No, yeah, what I was thinking was like, because you have like the vector of like, I think it's I, J, and K. Like if
Yeah.
you look at it vertically, like see that you were to like eliminate, I think it's I and then the two negative gammas. And if you were to eliminate that side, like the left side, and then the first upper
Okay,
part.
so yeah, are you suggesting to do the determinant, calculate determinant expanding over the column, or what?
Yeah, I think so. Where you're just left with like
Well, that
four
doesn't,
values.
that doesn't make much sense. So it's not gonna. So it is true that you can do it for the determinant, but the formula is not supposed to work like this. Like we should actually understand the determinant in quotes. Like it's really it's a prescription, if you wish, right? So here, because you see this I, J, and K, they are vectors, right? And alpha, the second and third rows, they are numbers, so they're not on equal footing. When you're doing the column expansion like this, so I think what you're suggesting to write is this, right? So let's just pretend that we don't care and write it like I multiplied by beta gamma, right? And then plus alpha multiplied by what? J gamma. Actually, here it still works, but we're actually not supposed to do that. So, but the reason why it works is really accidental. Okay, and then 1 minus alpha times minus beta k. So it still works, right? You still get the same components. So let's simplify it. So this is equal to I beta gamma plus j alpha gamma plus k alpha beta. So we do have the same vector here. Yeah, but yeah. So it works sometimes, but don't do that often. Yeah. So like it actually I mean it works on the level of the calculation, but like the way the formula is interpreted is should expand it along the first row. Okay. Other questions? Good. So that's the component of vector n, and now let's just find the equation for the plane. So yeah, we just do the. Sorry, that's somehow when I get an income call, I do put it do not disturb, and somehow whenever I have a call, I get my Zoom thing shut off. I'm terribly sorry for that. Meanwhile, you can find the equation. Yes. Start broadcast. Good. So yeah, so this is n, and what we need to do, we just need to do the and then yeah, we need another vector in a plane. So say this is R0, and then maybe R1. Let's take R1 to be 0 beta 0. So the equation of the plane would look like n dot R minus R0, which in this case will be exactly this vector alpha beta, right? So which is here is alpha beta. is equal to 0. Question from Hannah. Why is vector oh yeah, no reason. Yeah, thank you, thank you. You're absolutely right. Yeah, absolutely. Thank you. So and then which means that, so yeah, so the vector alpha beta we already have it. So alpha beta is minus alpha, beta, and 0. So we do the dot product of n and that thing. Right, which would look like so beta gamma, alpha beta, dot with minus alpha. Oh, I'm sorry, guys. I'm sorry. We need to write the formula for the. We need to find a point somewhere on the plane. I'm sorry. It shouldn't be that you just give you one. That just gives you 1 point on the plane. Yeah. So let's select any point. So this is not R1. Yeah, shouldn't be here. We need the equation, right? So we put some point P with coordinates x, y, and z on the plane, and then vector R, R1, will connect it, the origin to that point, right? So R1 is always, yeah, so R1 is always x, y, and z, right? So that's the point which will, instead of R1, you can plug in any point on the plane. Okay, so now, and R0 is alpha 0, 0. So that's how the calculation will do. So it's that multiplied by x minus alpha, y, and z equals 0. And if you do the calculation, you see it will look like this, right? So it's beta gamma x minus alpha plus alpha gamma y plus alpha beta z equals 0. Or we can expand it, right? So we have beta gamma x minus alpha gamma y plus alpha gamma y plus alpha beta z, and then minus alpha beta gamma equals 0. So you see there's some beautiful symmetric expression here, right? So if you look at it, there's some symmetry, right? So it's symmetric relative to interchanging alpha beta gamma in cycle and x, y, and z in cycle, right? Which of course is part of the symmetry of the problem, right? You can rotate the axis, you can replace x, y, and z cyclically, and then swap alpha beta and gamma cyclically. So which shows that the answer is legit, right? So it's is what you expect. It passes some sanity test. So in particular, if alpha equals beta equals gamma equals 1, right? Then you have this kind of face with a tetrahedron like that. So it's 1, 1, 1. Then this is n. Then the equation looks like this. It's x plus y plus z minus 1 equals 0. And vector n has components 1, 1, 1. So it kind of goes in the first octant, right, in the middle. Okay, any questions? good. Emma, if you write limit x, y, and z under 1, we get the solid. Limit, you mean the inequality, or the if you want to describe the whole tetrahedron? Oh yeah, right. So if you limit and between, yeah, that is true, right? So you would it would just yeah. So like if you vary alpha, beta, gamma from 1 down to 0, you will have covered the entire tetrahedron. Right? It's yeah, that's right. You can describe it this way. Okay, so that's how you can describe planes. Then now let's say we have 2 planes at once. Well, what can you measure with 2 planes? One thing you can do, you can find the angle between them. So so you get one plane that goes this way, and another plane that goes that way. And unless they're parallel to each other, they will inevitably intersect along a line. So you can ask yourself, what is the angle? What is the angle that made between them? Right then, it's not so easy to answer, especially you're just given just 2 planes like that, and you have to first define the angle, right? So which angle should be used, right? So it's like basically you need to measure the angle between these 2 planes, and then like how do you even define it? Well, the way you should define it is the following: you can measure the angle between the normal planes, the normal vectors, excuse me. So if this is n1 and n2, right? What you can do, you can measure angle between these guys and define it to be the angle between the planes, right? So that would correspond to what? To drawing the perpendicular line to this common line between these planes from any point of the plane, and then measuring angle between them. But it's much easier just to define it geometrically like that. So we just say that cosine of theta is equal to n1 dot n2 divided by absolute value of n1 times n2. Yeah. So in particular, let's calculate which angle is between the plane that we have just found, right? So like this angle over here. If you draw a line like that, so which angle is this plane, the plane we just described, let's call it P, makes with the XY plane. So N1 and N2 are each orthogonal to their respective planes. That is true, yes. N1 and N2 are N1 is orthogonal to the green plane. Yeah, well, N1 is orthogonal to its plane, and N2 are orthogonal to that plane. So it's like, yeah, like you can see why the definition makes sense if you just try to draw it on a plane, right? So let's do the same exercise for lines in 2 dimensions. They have 2 lines. Well, what is this angle equal to? One of the way to answer this question is you draw normal here, and then you draw normal there, and it will take you like you can quickly realize that these are the same angles, right? If you just calculate the angles here. Yeah, color coding is the same as is for the planes. I think, yeah, it just accidentally looks like the vector n1 is inside the green plane. I'm sorry if that was confusing. Okay, so, and basically this definition, it takes this idea to the next level, to 3 dimensions. So in the example above, we have plane, so vector n in red above, right? Let's keep the same color, was equal to 1, 1, 1. And we have vector k, which is the normal vector to the xy plane, which has components 0, 0, 1. Okay, so let's calculate. So cosine of that angle, let's keep called theta, is equal to the dot product, which is 1 times 0 plus 1 times 0 plus 1 times 1 divided by lengths of those vectors, right? So what is the length of vector n in this case? Square root 3, of course, right? It's square root of 1 squared plus 1 squared plus 1 squared, and vector k has unit length. So cosine is equal to 1 over 3. So it's not 45 degrees, contrary to the expectations. It's actually arc cos of 1 over square root 3. It will be 45 degrees in 2 dimensions, plane. Okay, good. So let's make a quick break, maybe. Well, let's continue at 11:10. Okay, and then you can collect the questions from the homework. We'll discuss them also. See you in a bit. Okay, any questions so far? Yeah, we can. I can finish doing this discussion of the planes and lines, and we can take questions on the homework. Or we can take questions on the homework right now. Yeah, so if you have any. Yeah, I do realize that this week we have less time, but yeah, so like I said, you can do the homework over the weekend, and then you can talk about this on Monday. Okay, so there's still time. Okay, another natural geometric question that you can ask yourself is how to measure a distance from a point in space to the given plane. So in other words, it will be the length of the line segment, which belongs to the line which is orthogonal to that plane, right? So if, say, you have a plane given by, so we know now the planes are specified by their normal vector and by some point on the plane. So say we have, so you have point P0, which is on the plane, and then there's a point P1 somewhere in space. X, Y, Z, and say the plane is given by equation AX plus BY plus CZ plus D is equal to 0. Right? The question is to find the distance. Distance from a point to a plane. That was too close to the previous writing. So if the plane is given by this equation, then we know that the normal vector, we know what are the components of the normal vector are. And so, right. So yeah, we can draw this line. There's a 90-degree vector, and then say there's a vector B that connects P0 and P1. Okay, and yeah, so what we need to find is this distance here, this D. It's the length of the vector. So normal vector to the plane can be either up or down, it doesn't really matter. Let's say it goes up here. So therefore the distance is, so this distance will be the length of this line segment, okay? Now, well, if P0 has coordinates x0, y0, and z0, right? So then the vector B has coordinates x minus x0, y minus y0, z minus z0. And what's the quickest way to express the distance? Well, it will be, in other words, the D. Okay, so we can get this vector D. So this D here, not vector, because it will be the projection, right? It will be the scalar projection, as we discussed it before, a component of vector B on the normal vector n. Right. So in other words, the scalar projection of B onto this thing is D, right? Or it's like if this angle is theta, it will be d times cosine theta. That's right. And we know how to calculate the component. We talked about it last lecture, I believe. So it's n dot b divided by n. And so it's you do the dot product with n and then you just divide by the absolute value. Okay, and well, we just know what this is, right? So n has components a, b, and c. See, for this calculation, this free term, free coefficient does not appear. But implicitly, of course, you know about this, right? Because you know the coordinates, you know the position of point x0, x0, y0, and z0. So you dot this with x minus x0, y minus y0, z minus z0, and divide by the length of n, which is, of course, square root of a squared plus b squared plus c squared. And that gives you ax minus x0 plus b y minus y0 plus c z minus z0 divided by root of a squared plus b squared plus c squared. Okay, now if you actually want to include the d into the formula, we can do that, right? Well, how can we do this? So this equation, this distance formula requires you to know the position on the requires you to know the position of point x0 on the plane. But we know we can impose this equation, right? So in particular, this equation holds for point x0, y0, and c0 on the plane. So if we simplify the numerator in this formula like that, as follows, we can actually include the d into the formula. So we can get, I'm just going to open up the parentheses and move everything to the left. So it's ax plus by plus cz, then minus ax0 plus ay0 plus cz0. Okay, and divided by this root. And from the equation of the plane, this parenthesis with the minus sign is equal to d with a plus, which reads, so therefore we can write it as ax plus by plus cz plus d over root of a squared plus b squared plus c squared. And this is the final formula, right? So notice that it only depends on the coefficients of the plane and the coordinates of the point from which you want to draw find the distance. Let's look at an example. In fact, let's get back to our favorite example with this tetrahedron. Maybe I can draw it again. And since it's a discussion, maybe I should let you do some of the calculation. So let's draw again this tetrahedron. So we have the plane like this, given by equation x plus y plus z plus 1, right? So plus 1 is plus 1 or minus 1, I forgot. I think it's minus 1. Minus 1, yes, minus 1. Equals 0. So find the distance from the origin. There's some perpendicular that goes here, right? So distance from O to this plane. Okay. That's right. So here the calculation is really quick, right? It's if you use this formula, right, we can plug it in here. So the yeah, so the coordinates and yeah, and actually I forgot something important here. The there's an absolute value, right? So here you see that the distance becomes negative. So it has to be an absolute value because it's a scalar projection. Yeah. So d can be negative, as is the case here. So x equals y equals z equals 0 in this case because we are looking at the origin of the coordinate plane. So it's 0 times 1 plus 0 times 1 plus 0 times 1 minus 1 absolute value divided by square root 3. So it's also 1 over square root 3. Yeah. Which is what? It's like the third of the diagonal, right? So if you draw a cube, right? If you sort of reconstruct the cube here with sides 1, 1, 1, like that. So the cube can be cut into tetrahedral like that, and then if you draw the diagonal that connects O and the opposite vertex, its length will be square root 3, right? And that's the that will be 1/3 of that, right? So you can put 6 tetrahedra like this in the cube if you sort of pack them properly. Okay, any other questions? Do you want to talk about any homework problems from week 2? Or do you still need more time? Okay, yeah, sure. Yeah, that's totally understandable. Yes. Okay, so now, yeah, we can talk about. There's one topic about quadratic surfaces in this week, right? And also the stuff about vector functions, right? So, what do we want to do now? So surfaces or vector functions? It can take. Yeah, we can look at surfaces just for fun. I think we can make some plots in Mathematica. Right. Okay, good. So let's do quadratic surfaces. And then perhaps we can just start vector functions next class. It's okay. Next week. So a surface, right? It's a two-dimensional shape inside 3 dimensions. Sort of more formally, surface we could define surface as something that looks locally like a plane, right? So one of the examples of surface is a sphere, and so you have a sphere. If you really zoom in on a sphere, on the surface of the sphere, like draw a line that is tangent, the plane that is tangent to it, and sort of zoom on the vicinity of this point, it would look flat, right? I don't have to explain it to you. We all live on a big sphere, right? And even some of us, well, not of us, but some people on Earth think that Earth is flat, right? So, so they take the idea to extreme. Now, yeah. So the joke about flat Earth, it's like there are supporters of flat Earth theory all over the globe. Yeah, so the plane is one example of a surface, but of course there are more interesting examples. When I say quadratic surface, it's a surface that is described by quadratic equation in x, y, and z. So this is what it is. So it's given by this equation: a squared x squared, a x squared plus by squared plus c squared plus d xy plus e yz plus f xz, and then linear terms plus gx plus hy plus iz plus j equals 0. Absolutely, there are zillions of proofs that Earth is that Earth is round, right? Sort of. So indeed, so probably the simplest one would be yes, like what you're saying is that the fact that atmosphere, like the signal would reflect from the atmosphere, and then you can reach points which are not visible by a direct line, right? Yeah. Yes, that's one of the way to prove it. Yeah. How else you can show that the Earth is round? But yeah, actually, if you actually try to construct a flat Earth like that, if it would have the same mass as Earth has right now, it will be gravitationally unstable, right? So like, Earth is heavy, right? It curves the space around it significantly. So we can measure the curvature. We can measure the general relativity effect of the curvature of Earth with our devices, right? So your GPS on your phones is adjusted for the fact that the time slows down when the satellite is in orbit. Gravity when the satellite is much weaker. It's a little bit weaker than at the ground level. So in the calculations of the position of your of the point, you need to adjust for that. So if you try to put the Earth into like a pancake with the same mass, it will just cripple and collapse into a sphere. Anyhow, I have a personal video from one of my dads. Are interested in credible source. Okay, sure. Yeah, sure. If you want to share it, yeah, we can have a look. Right. Yeah. So this equation here that we just wrote, see, doesn't even fit into one line, right? It's really long. And there are zillions of particular cases, right? So for example, well, we discussed some of them already, right? So if we only focus on these three coefficients, so if you put all coefficients to 0 except a, b, and c, and say if a equals b equals c equals 1, which surface is that? Probably it's not the best color. Yeah. Now, I'm sure Berkeley students do not believe. Yeah, it's a sphere, right? It's a sphere. Yeah. Yeah, I really know what this society comes from. We just probably they want to push it to the maximal level of absurdity, like how stupid the idea can be, so that you can collect people around it. Yeah. So this is a sphere, and then yeah. So how about this? It's a little tricky question, but nevertheless, how about that? D equals E equals F equals 1, and the rest are 0. Which surface is that? What your gut feeling tells you. It's still quadratic, right? There's still some, it just, they have. Actually, when I said equals 0, we have to be careful. We also need to keep j. Yeah, I'm sorry. Even in the first example, so this is equal to 1 and also j is equal to 1. Actually, no, j, I'm sorry, j is equal to, say, -1. Right. So because, okay, yeah. Right, so the, let me come back a little bit. So for first question about the sphere, a equals b equals c equals 1 and j equals to -1, it will be sphere of radius 1, right? Now here, d equals e equals f equals 1 and j is also, and j is still -1, right? So j is -1. Then we'll talk about what happens at when j is equal to 0. So how about how about this equation? Xy plus yz plus xz equals 1. What does it do? Well, to see what's going on, you may want to change the coordinates a little bit, right? So if you are if you are puzzled by this, or try to answer the same question in 2 dimensions, right? So in 2D, the circle is given by equation x squared plus y squared equals to 1. But what if I say it's xy equals 1? It will be some hyperbola, right? Sort of. Yeah. Now, what do you think will happen here? It's like 1 over x shape revolved. It might, yeah. So that may not be, you may not be able to show it right away, but yeah, it could. Yeah. So yeah, let's leave it for so let's see how is there a way easily to go from this equation to that equation. So we can change variables. So let's say x is equal to x prime plus y prime, and y is equal to, prime is not a derivative, it's just another letter, and y is equal to x prime minus y prime. From the point of view of linear, from the geometry, what does this transformation do? So you have xy, right? You have a hyperbola, xy equals 1, it's like this. It's like that. So take a different color. Okay, and now, so that's written in xy coordinates. Now, xy equals 1, in this x prime y prime coordinates will give you x prime squared minus y prime squared. Right, so you have a new equation, x prime squared minus y prime squared equals to 1. Right, and if you had to draw it, it would look like this, right? So it's okay. So we can see that this transformation from this written in, this is x prime y prime. This transformation, you can write it as a matrix, right? It's a in terms of linear algebra, it's a matrix which has the following components, and it's a rotation by which angle, right? So you rotate this coordinate system by pi over 2, right? So you're doing the pi over 4, right? So you're doing the 90-degree rotation, and then you can see that this hyperbola in the first coordinate system, it will look like first and third quadrant, and in this black picture, it looks like up and down. So yeah, so this is hyperbola, and most likely that thing. So as you're suggesting, it would also look like hyperbola of some sort, right? In fact, to show that it will look like now it's not going to be hyperbola. It will be the so-called hyperboloid, right? Because it's a surface. Yeah, and then we'll see exactly how this works. Okay. Now, well, we already know how so if you only focus on this part of the equation, what is this? Which surface it describes? If H, G, H, I, and J are non-zero and the rest is zero, it's a plane, right? Of course, if it's a plane, we know that. So linear surfaces, these planes are part of the equation. Okay, and how about this? So A equals B equals C equals 1, and everything else, including J, is equal to 0. So the equation is x squared plus y squared plus z squared equals 0. A point, right? So that gives you a point. Now, how about let's see. So what else is sort of the boundary point? So how about E equals how about E equals 1 and the rest is 0? So the equation is yz equals 0. What's that? So intersection of two planes, which ones? Two curved sheets. Yes, so y equals 0 and z equals 0. So the way to see it is okay. So let's wait for more answers to come in. So Hannah is saying it's y equals 0 and z equals 0, right? So indeed, so to solve it, you need to, it's either the product of the numbers vanishes. It can happen when either of them is 0, right? So it's either x equals to 0 or y. There's no x here. Right, so it's either y equals to 0 or z equals to 0. So y is equal to 0 is a plane, and z equals to 0 is a plane, and they would intersect. That's right. So that happens for and then how about E equals 1, and then J is equal to say 1, right? So we have yz plus 1 equals 0. What's that? So you wouldn't hesitate to answer this question in 2 dimensions. If you say y and z are coordinates on a plane, then it will be some kind of a hyperbola, right? But the now what? Now it does not depend on x at all. What does that mean? Curved plane, sort of, right? Good. So is it one curved plane or 2 curved planes? 2 curved planes. Yeah, right. So I think what Alex is saying is this. So let's forget about x for a second and then draw it in the yz plane, right? So yz, and so y dot z equals y times z equals -1, right? So it looks like a hyperbola in second and fourth quadrants, right? You just negate this, and now you just add x-axis to this. So what happens is that you would have like 2 sheets that look like that, right? So it's like will be 1 sheet here and then 1 sheet here. Which would sort of continue, extend indefinitely, extend to infinity in x direction. Okay, so as you can see, this equation has a bunch of parameters. So how many? That's 10 coefficients, right, from a to j. And in principle, one should investigate all possible values of these parameters. And indeed, there's a bunch of particular cases. Some of them we just discussed right now. So I'm not going to bore you with sort of sort of exhaustive study of each of them. You can read it in the book. You can play with pictures in Mathematica. But we'll talk about a couple of more important ones. And then yeah, so we'll do some calculations with them. So yeah, so basically you can have stuff from like a point to intersecting planes to intersecting lines, etc. Okay, let's find some shape that we haven't seen before. Let's do one cubed equation. How about this? Say I want to do a equals -1, b equals 1, and I, its coefficient in front of z, is equal to -1, and the rest are 0. So if you do it like that, it would look like, so we can move it, convert this surface as z equals a y squared minus x squared. What do you think that will be? How would this thing look like in space? Saddle shape, yeah. So Bennett, can you describe a bit more why is this the case? Right, indeed, so it looks like an actual horse saddle. So where it's, yeah, explain a couple of, or you can unmute yourself and explain it. It's like hyperbola, but in 3 dimensions. Well, I mean, that doesn't really help, right? Because we just saw a hyperbola in 3 dimensions that doesn't look like a saddle at all. Well, so let's think about this shape as, so we don't have to sort of envision it at once. Let's just try to slice it with different planes. Yeah, I know. It's a bit sort of not so easy to explain once you kind of get the idea. So it's actually not that hard to visualize it if you do it sort of step by step. So first, let's look at surfaces, excuse me, planes with constant values of x, right? So need some more space here. Right, so x, y, and z. So when x is fixed, right, so say x equals some constant, say x0, right, the equation looks like a z equals y squared plus a constant, minus a constant, right? So in particular, once this constant is equal to 0, so you have z equals y squared, right? So x equals to 0 means that we live in the yz plane. So in the yz plane, we have equation z equals y squared, which looks like this, right? So there's a parabola here. Now, what happens if we step off from this x equals 0 position? So we now say at a position at a say x equals 1, for example. Well, then we have equation z squared equals y squared minus 1, which is also a parabola, but it's shifted down by 1 unit. Okay, I'll do my best to try to draw it so it looks like. It looks like that, right? So, and then if you step to minus 1, right, because it's a squared, it will also be a parabola that goes down. So like on the other side, the parabola sort of, it will go under the thing. Right, and then the farther we go either to plus infinity or to minus infinity in the next direction, the further down we shift it, right? So the next parabola would look like this, and the next parabola would look like that, and like that. And the same thing, so it forms like a valley of the river, or like part of the saddle thing. Yeah, and then it would sort of, walls of the saddle extend over here, and it would sort of drop also in the other direction, in the negative x direction. Okay, and now we can do the same exercise with a constant y section. So if you slice this picture with planes at constant y, right? So then we'll have inverted parabolae, right? Because it's z equals constant minus x squared. So when y is equal to 0, we have an inverted parabola that looks like this. And as we shift from the y equals 0, they'll rise. They will go like this. And same thing for with the others. Right, so that gives you a saddle. It's a saddle, or scientifically it's called sort of, it's the one-sheeted hyperboloid. One-sheet hyperboloid. Yeah, that's right. Yes, it's a surface that appears quite often. Well, if it's one-sheeted hyperboloid, there's also a two-sheeted hyperboloid. and it's given by a slightly different equation. So for that, we need to add more things. Now we need to look at a couple of possibilities here. So first, let's do yeah. So let's say we have this coefficient, so a x. Let's focus only on the quadratic part. 1 plus c z squared plus d equals 0. That's only work with these guys. Now, if a, b, and c are positive and d is negative, we have an ellipsoid, right? So a, b, c positive, or like they have the same sign. Like basically a, b, c have the same sign, and d has the opposite sign. Yeah. Have the same sign, and d has the opposite sign. That gives us the ellipsoid. Right, so it's this kind of melon shape over here. And now things will change as we try to alternate signs, right? So the basically what we care about is the relative assignment of signs d with the a, b, and c, and then how many pluses and minuses are inside a, b, and c. So we can start with the situation when d is equal to 0, and then sort of we'll deviate to the left and to the right of that, right? So let's say when d is equal to 0, so we talked about the case when a, b, and c, and d, a, b, c, and d have the same sign. That gives us a point. But how about now we have something like x squared so let me do the other notation. So let's say we have little a. So assuming that little a is bigger than 0, right? So we have little a plus little by is equal to little cz squared, where they're all positive, right? So a, b, and c they're all bigger or equal than 0. Oh, no, just strictly bigger. So like this. What would this thing look like? If you're in doubt, again, try to simplify the problem by looking at 2 dimensions. So take a slice. Take a slice of constant z or constant x or constant y. Slice perpendicular to x or y-axis hyperbola. Yes, okay, very good, yes. Slice perpendicular to the axis, ellipse, yep, that's right, of course. Yeah, that's true. But what happens, very good, yeah, so now do you remember we talked about this in the first week. So hyperbola and ellipse are sections of what? So what I'm describing is that we have some 3D, some surface such that depending on how you slice it, you have either hyperbola or ellipse. Which surface was that? So ellipse, hyperbola, the cones. Yep, that's right. Well, we don't call them two cones. It's just the cone. The cone has two lobes, right? Indeed. So this equation describes a cone surface. Let's try to draw it. So right. Oops, sorry. So now it's not like it's a slight modification on that, because the section parallel to the, as Hannah was saying, section perpendicular to the z-axis or parallel to xy plane will be now an ellipse, right? And then in the cone example that we had last week, it was a circle, but it's okay. Just we simply stretched it along the x and y directions. That's fine. Yeah, and then of course, if you slice it with a vertical thing, you will have two hyperbole, right? So, well, you just write it here as so. Say x is a constant, right? So x is equal to say x0. Then we can write the equation, right? So they have by squared minus cz squared is equal to some constant, which is yeah, actually, do you want to do it another other way around? Oh, that's fine. That's right. It's equal to minus a x0 squared. So you can write differently. So this is a hyperbola, slightly distorted by those coefficients. But what if x0 is equal to 0? What if x is equal to 0? Well, then we have this equation, right? by squared is equal to cz squared. What does this equation represent? The last one. Two lines, yeah, absolutely, right. So because indeed, the solution for this equation is y is equal to plus minus square root of c over bz. So these are two lines which are the which belong to the cone at the plane given by the equation x equals to 0. So these are the lines you can do that. You can show the same for every plane that contains a z-axis, right? So if you slice it with a plane, so it goes like that, it would so yes, it intersects it somewhere here. Right, so we have this line and then that line. And so this is two pair of the green lines are given by this equation. Yeah, so this is a cone. Okay, good. So if d equals 0, this is a cone. D equals 0, and then one of the coefficients, say c is less than 0, and the others are bigger than 0. Of course, you can switch it, right? It doesn't really matter. What matters is that only one of the coefficients. So if d equals to 0, it doesn't matter how many minuses you have, 1 or 2, right? Because there are 3 overall. Okay, what else can we do? Now let's say keep the equation. Say now a bigger than 0, b bigger than 0, c less than 0, and d is equal to, and d is also less than 0. So we can write this as ax squared plus by squared minus cz squared is equal to d, where all the small letters are positive. What's that? What's this equation? What does this equation represent? Again, look at sections, at cross sections. I think I need to leave like 10 minutes or so. Yeah, so we have we can talk about that and conclude with the surfaces. So what's the constant z? What's the plane perpendicular to z section gives you? Put z equals constant. What is it? An ellipse, right? Are you going to get an ellipse for every single value of z? Will it always be an ellipse? Yeah. So ellipse. So right. So then, so you have c. Z is equal to constant sum z0, and because the coefficient c is positive, we are guaranteed that if you write it like this, plus cz squared, right? And this is always positive. And because it is positive, that we're always going to have an ellipse with some of some size, right? For some values of its major semi-axis. So at which values of z the ellipse is the smallest, and what happens as we go to large z and to small z. So eccentricity, I don't think depends on z though, right? Amog. So eccentricity is the depends only on a and b. What depends on z is the overall size, right? So if you let's call this whole thing r squared, right? And then you can write the equation for the ellipse as x squared a over r squared plus b y squared over r squared equals 1. And eccentricity is the ratio, is this, right? It's root of 1 minus b squared over a squared. And then, oh, no, not b squared. Yeah, so like here, the r squared will cancel. So the contribution is an overall factor that does not change the eccentricity. So anyhow, so we have some ellipse at z equals 0. What happens with this ellipse as we go up? Larger, right? So larger ellipse if we go up or down, right? So because of the absolute value. So ellipse will be larger, yet larger, and here it's also larger and larger. So the shape would look like this, right? Just like a tornado kind of mirror to kind of thing, yeah. It's like a funnel, like this tornado shaped funnel, and that is the one sheet hyperboloid. So it does look like a hyperboloid, and I think someone should said that you can get a hyperboloid by rotation, right? So and indeed, so the let's look it down. So it's one sheet hyperboloid. So the yeah, so we just talked about constant z sections that give ellipses, but well, constant you're always gonna get a hyperbole if you do say constant x sections or constant y sections, right? So that thing, so that is a part of hyperbola, right? So like its surface, right, is so these are hyperbole. You can do that. Good, and then probably the last thing we can do, the last surface is gonna get in. Right, so let's do one more. Say we have this equation. So we have ax squared plus by squared minus cz squared plus 1 equals 0, like that. What's that? It's going to be. Also, yeah, maybe one comment before the on the previous example, which will also apply to this example. Actually, no, okay, never mind. Yeah, it's not going to help. Yeah. So let me keep them both. Yeah. So what we did, we altered the sign of d here, right? So let's put a d. It will be consistent. So before d was, yeah, we had the plus d here. Okay, so what effectively was changed is the sign of the d factor. The rest is the same. No, you can have any. So if z is small, right, it can be smaller than 1. I guess what you're asking is that is there always a solution, right? It doesn't have to be. So if square of something is negative, then there are no points in that range. Okay, so maybe a quick question. Okay, is it like that the last example, but with a portion of the middle cut out? Sort of, right? So indeed, so in the middle, by middle you mean some range in Z, right? Yeah, so indeed, so if Z is small, right, there might not be a solution, right? So you can find how much, by how much, sort of what's, yeah, that's right. So that inequality should be satisfied. If this inequality is satisfied, then you have a solution. If it's not, then not. So we expect to have two branches, sort of two lobes of that shape. Now, how would the shape would look like? So, I mean, you cannot just cut that thing that we had before, right? It has to be smooth. It would look a little bit different. But yeah, there will be two shapes, one in the positive Z half space and another in negative Z half space. Obviously, it will be symmetric because Z to the minus Z is the symmetry. How would each thing look like? Again, we can look at slices, right? So we can slice at constant Z position. So the inequality that Amlog is saying, so when it's saturated, when D is equal to CZ squared, you're just going to get 1 point, right? There will be like a single point. And as we go higher than that or lower than the minus that, what will be the cross section at constant D? So say Z is larger than that, right? So you can move it to the right-hand side, it will be a positive thing, right? And you have equation for the ellipse. So when Z is larger than that value, right? So yeah. So this is, here is a point plus root D over C. And here it's minus root D over C. And then above that, we have ellipses, intersection, and then kind of here it's a point, and then these ellipses, they start to grow, right? And here also, like the same happens at the bottom. There's a point where the ellipse degenerates, and here it's a bit bigger, and here it's a bit bigger, and it goes. And then you can also find the shape. If you slice this with, say, constant, say y equals 0 plane, then of course you will see that it should be a hyperbola, right? So the that curve, which defines the shape of those things in other directions, like this, they will be hyperbole. So that's another two-sheeted hyperboloid. Okay, great. So I think we should stop here. So you can, I encourage you to do as much homework as possible over the break. Of course, you may have some plans to go somewhere, although traveling is obviously limited. Yeah, so look at the exercises in chapter 12, and on Monday we'll start with a Q&A session. It will be like an office hour. I'll make an announcement. Okay. Any questions before we go? Will the next quiz will be on chapter 12? Yes, that is correct. It will be on chapter 12. I think we'll move. No, today we didn't talk about vector functions, so that will be the new material for week 3. Good. Okay, thanks, guys. See you next week. Bye.